Yeah, warm welcome to the participants and the speaker. Welcome to the Day 2 ATAL sponsored faculty development program on additive manufacturing. So today we have a speaker, Dr. N.M. Kumar is with us. So he is an associate professor in mechanical engineering department at National Institute of Technology, Warangal. He obtained his bachelor degree in the mechanical engineering stream from JNTU, Canada in the year of 2000, and he joined masters in computer integrated manufacturing, joined in PSG College of Technology and got the degree in the year of 2002, and PhD in mechanical engineering stream from Osmania University, Hyderabad in the year of 2011. So immediately he joined for the postdoctoral fellowship in the area of 3D printing at Milwaukee School of Engineering, United States of America in the year of 2012. He has supervised more than 30 MTech projects and produced 4 PhDs and guiding 4 more PhD theses. He has published more than 70 research papers in national and international conferences and journals. He has filed 1 international patent and 2 Indian patents in the area of 3D printing. He is instrumental in setting up a rapid prototyping laboratory at NIT Warangal. He started MTech program in additive manufacturing in collaboration with CMTI Bangalore, first time in India of its kind. He has established a world-class metal 3D printing facility at NIT Warangal under TechCube 3 grant. He has conducted more than 15 training programs across the India and trained around 900 participants in the area of 3D printing. He received Young Engineer of the Year 2009 award from the Government of Andhra Pradesh and the Institute of Engineers, India. He has executed sponsored research project for the worth of 1.24 crore in the area of 3D printing. He is the life member of ISTE, IE and RPSC societies, and he has visited several countries like Australia, Sweden, Singapore, Finland, France and USA for his research experience. Sir, the session is yours. Over to Ravi Kumar, sir.
Yeah, thank you, Prabhakaran and Dr. Vinod, the coordinators of this program, and very good morning, one and all. So first of all, let me thank the organizers given me this opportunity, and of course, thanks to my guru, Dr. P. Radhakrishnan sir. I was there quite some time at PSG Tech as a student as well as an employee in a TIFAC core center. That is during 2001 to 2002 as a student, and then followed by a project engineer at TIFAC Center. So I'm very much excited that I'm the part of this program. Yeah, first of all, let me thank the opportunity given here. Dr. Prabhakaran, can I share my screen actually?
1 second, sir. 1 second, sir. I will give a share option to you.
Yeah.
1 second, sir.
Yes.
Sir, I think now you got the option to share your presentation.
Yes, I got it. Yeah.
Yes, thank you.
My screen is visible?
Yes, sir.
Thank you.
Yes, sir.
Thank you. Thank you. So very good morning, one and all. So it's nice to have the session at PhD Tech. So as it is my actually almeta, and then here I worked for some time, and say, yeah, and coming to the talk. So yesterday, the speakers might have given the introduction to this additive manufacturing technology. So my talk, so majorly focused on the yeah. So my talk focus will be on the data formats of additive manufacturing. So as we know that additive manufacturing is a technology which needs a design, basically, which is derived from a digital data. So that digital data, in which format that it should consist of. So my talk will be basically focusing on this data file formats aspect. And coming to my outline of my presentation, so giving a bit of introduction to additive manufacturing and a bit of introduction to design tools. So I can see the some sessions is focused majorly on these design tools. So from the schedule just now, I realized. But anyway, my focus it need not be on these aspects, but design tool is needed for generating a data format. That's what. So then I'm going to give a bit of introduction to the design tools and the data format, so that any additive manufacturing system can understand only the STL file. That is, STL stands for stereolithography, and it was the format invented by the Charles Hull, who incidentally the father of this technology, or rather than he filed the first patent and then commercialized the machine, the additive manufacturing. Now we are saying this technology, but now, but previously it was the name of rapid prototyping. So the STL file, when this technology started, that is the late 80s, so 1988, 89 time. So now also the data format so is STL file as a de facto standard. So though you have other data file formats also. So my talk will be revolving around this the STL file format, the advantages, though it have the advantages, but it have several problems and several challenges that the STL file typically having. And then recently ASTM has proposed a new file format called AMF, that is Additive Manufacturing File Format. So, and then this will address the problems or the challenges that the typical STL file is having, but it will be addressed in AMF file format. That is recently ASTM F42 committee has say proposed this format, and I'm going to discuss the AMF file format, and then the future additive manufacturing data file formats, what could be. So my talk will be based on these topics. So then let us start with a bit of introduction. I know that it is the second day. Probably the earlier speakers might have given the introduction to this technology. Say a typical additive manufacturing, it has to start with the CAD model or the digital design, so that it has to say start the journey of additive manufacturing with the digital data. So that is to a 3D CAD modeling, the route, the procedure. So you can start your if you want to make an aircraft, so then it should come in a digital format. So one way of getting a digital data, maybe through a 3D modeling or a 3D CAD modeling, typically you call, or geometric modeling, typically you call. And for that, you may have some workstation. But nowadays, even an Android based device can also be supported some of the modeling softwares. But anyway, we need to start this modeling part initially to get a digital format, file format of a typical product that you are trying to fabricate by using additive manufacturing technology. And then we need to convert that data and we need to transmit that data. Why do we need to convert that data? Means that is our talk now. So the additive manufacturing machine cannot understand directly your CAD model. Typically, if you're using CATIA, or you may be using Creo, or you may be using a SolidWorks or any other say package, but each package will be having its native format, like it may be a dot PRT, or it may be dot SLD PRT, or it may be dot DWG. So then you may have a different file formats that depends on the package that you're using it. But additive manufacturing machine cannot understand dot PRT or a dot SLD PRT. So it can understand only the STL file. So that's what we need to convert your dot PRT into an STL file, basically. So then once you're done that conversion, we need to transmit that data where you have additive manufacturing machine. So, and then that additive manufacturing machine may have an interfacing software. So before you transmit that data to that software, we need to check, or we need to do a kind of say errors, if there are some errors, maybe in STL file. That also we'll discuss now. So we need to check that STL file before you prepare the code. So basically, if you are coming from CNC technology, you know the importance of generating a G code or M code. So G code, M code kind of a stuff here, we need to generate a build setup. So that is sent to the machine. So you have an additive manufacturing machine here. Then we need to prepare a code. So that code will be send it to the machine. So then once you prepare that code and sending it to the machine, so as for that code or the instructions, so it is built layer by layer. So basically, as we know that additive manufacturing follows a layered manufactured approach. So one layer upon other layer. So it is going to slice the model. The STL file is getting sliced and generating a layered data, and that layered data is physically realized here. So, and then once you complete your layer by layer fabrication of your, say, typically you have a product, that product consists of some 100 layers. So then a layer 1 to 100 layer. So the physically, the joining of those layers will be happen in your additive manufacturing machine as for the code that you have generated, either in terms of fixing the orientation or the support generation. And then we need to slice that data into layers. So then once you specify the parameters like slice thickness and the support generation, and say we need to generate the tool path. Typically, there is no tool here. It's a toolless manufacturing, but the name is inherited from the CNC technology. So typically, the tool path is nothing but the code, or if it is a laser machine, the laser has to, say, travel as for the cross section that you have, say, generated in the computer or in the software. So based on that code, So it is getting fabricated one layer upon another layer. So then you may have a different AM process. I hope yesterday Dr. Sridharan might have covered all the AM processes. So let it be any process, and then your product is ready. So once you have completed your 100 layers and your product is ready, then we need to finally do a kind of a post-processing, say, step. What is that post-processing is, again, it depends on type of AM machine and the application where your part is going to. So then it can be a UV cured oven, that is for an SLA based system, or a VAT based system, which we need to further cure your liquid. Basically, SLA or a VAT system, the raw material will come with a liquid form, and it should further made 100% solidification through this final step called UV curing. So if it is a powder bed system, so you may have a different post-processing method, and if it is a jetting based technology, so you may have a different post-processing method. And then sometimes you may use ultrasonic cleaning or chemical cleaning, or some special devices you may use to do this post-processing, or even it can be a furnace treatment to further improve the properties, your mechanical or metallurgical or physical properties. Then it may undergo a heat treatment analysis also, heat treatment process or heaping process, or typically. So that purely depends on the type of technology you're using it and the application. So what is the accuracy level you're looking at? Because additive manufacturing machines as built, typically you may get around say 10 to 20 microns. That again depends on the different AM processes, but still you are looking for a mirror finish. So definitely you have to go with a specific post-processing method. So with this background, now we'll move on to the next slide. So the focus will be on the say data file formats. So let us start with some design tools. So AM design tools. So that can be either even a reverse engineering. I hope maybe next session there is a reverse engineering. So I don't want to spend much of the time here. So one of the methods may be a 3D model capture through a reverse engineering approach. Also, you can capture your physical object by using any digitizing systems. That may be the one method, and you may use some tools or the softwares to process your data. Or if you are coming from a CAD design procedure, like so CAD modeling approach, so then you can adopt different tools that you can getting started your product modeling or the designing aspect. And then we need to do, as we know that the CAD file, it should be converted into an STL file. STL file basically a triangular mesh. So that mesh should be repaired sometimes. So then we need to adapt some tools like Net or Mesh Mixer, Mesh Lab, or Magix software. You have plenty of tools available to do a mesh repair kind of a stuff. And once it is done repairing, and we need to slice that data, the STL file, and further repairing the mesh, and then finally we need to slice that model. And for doing slicing, you may have different tools. Nowadays, these tools are open source, like if you take Cura or Repeater or Simplify 3D. So all these are open source softwares. So, or it may be specific proprietary software which is given by the machine vendor. So then you may use any slicer software to do that slicing job. And nowadays you may have some digital libraries to do this. Existing models you can download from the community or repositories. So like something like a Thingiverse or a GrabCAD. So you have a plenty of tools. I hope maybe you have a separate session to discuss on that. But this is a typical scenario normally you will come across. So CAD design tools, I hope you are very much familiar about 2D modeling, 3D modeling. So then you may use these tools maybe in order to say start your modeling. Say you may use Blender software. You may use, again, depends on the domain that you are from. Like maybe you are working for some freeform modeling or artistic modeling, or basically some kind of animation stuff. Then you may adopt different tools, or you may use even a mechanical engineering software like this. So it depends on the type of product that you are looking at to be modeled, and then you can adopt any one of these CAD tools. And nowadays you have Onshape. There is a one open source software. Even it may work for Android based devices also. So then you can make use of any of these tools to get started your modeling of the product. So, and then you have a unique advantage once you come to the additive manufacturing technology. Once you adopt additive manufacturing technology, so then we can exploit the topology optimized structures can also be built. So the fabrication of your, as we know that you have several developments under this design philosophy or the design approaches. Like previously, it has started with a parametric modeling. Now you have a generative designs, topology optimized lattice structures, bionic designs, or biomimicry, where the designer may be taking inspiration from the nature, maybe in terms of lattice structure, or maybe in terms of cellular biology or the cell structure. Or light weighting of the structures in case of aerospace industry or medical industry, where you may reduce the weight of the products. So in that case, which you may adopt any one of these design approaches in terms of topology optimization, or in terms of lattice structures or bionic designs, or it can be a generative design to consolidate the parts. So then finally it should be getting fabricated, or finally it should be manufactured. So how do you get manufactured these nature inspired designs? So then of course the additive manufacturing is the solution, only one solution. Why? Because traditional manufacturing methods may very difficult to do, or difficult to machine, or difficult to cast these kind of nature inspired designs. Of course, additive manufacturing is, I hope maybe other speakers may be exploring all these tools. I don't want to go in depth into that tools. But why I kept here is it is interlinked to the data structure, the data file formats. That's what my intention. So then you may have several softwares, other tools to do this topology optimization, which I have listed here. So it may be, some of them may be open source, some of them may be proprietary tools that are available. So even you can come with a 3D model capture tools like reverse engineering, like you may use several say scanning devices, or the sensors, several sensors to capture your data. So then our job is to get an STL file. So then once you get a point cloud data, and then our job is to get STL file. So why? Because additive manufacturing machine can take only the STL file. So then you may use several sensors to collect your data in typical scanning devices. So then you may have several tools or the softwares to do this job, to reconstruct your product from digitized point cloud to the a 3D solid model, or a surface model. So, but our intention is to save that data into an STL file. Even you may have some repository tools, means some digital online libraries, which you can download these STL files or your CAD files in step format, or IGS, or .prt, or any other file format, which it will be. So in this case, we are not even modeling, or we are not even scanning it, but typically you may make use of these repositories or online communities to download these designs, maybe to name a few: GrabCAD, Thingiverse, and you have other several places or the communities or the digital libraries or the repository systems which you can download your models free of cost. And of course, you have another domain where medical domain. In the medical space, which we take from a digital X-ray or a CT, that is computer tomography, or a MRI, that is magnetic resonance imaging for different tissues. So maybe bone, maybe soft tissue. So then you can get it started your data, collecting the data through a CT or MRI scan, and further it can be reconstructed into a three-dimensional model, basically an STL file. So you can save your model, which initially it was in a grayscale images, which is collected through a CT scanner, and now it has a STL file, which is of a surface model or a solid model. So then that can be further explored or further taken into a CAD domain or a CAD software to do some design of an implant or to do some simulation of these implants that you have designed for a patient specific information. And then you may have even a 3D model, computer model, or FEA analysis. You want to, orthopedician has designed some implant, and then he needs to check for the loads and the failure of the implant or the bone. So then you may use FEA or CFD analysis in case of cardiac or in case of a neurosurgeon. So then you can take this data into a CFD package also, or even you can make a physical model through additive manufacturing technology, or you can do some design validation. So based on the design developed implant or a prosthetic or a device, so for that matter, which is specific to a patient requirement. And you may have several tools to do this job. So right from the proprietary softwares, mimics, to the open source software like 3D Slicer, so which will do this job. And then we'll focus on the STL file. What is the file structure of an STL file? Typically, as we understood, like we need to have the importance of converting your data into an STL file. But typically, if you say a domestic printer or an office printer, so the office printer, so you may be able to print a document, or you may be able to print a PDF, or you may be able to print an IGS file, or it may be JPG file, or any file format that printer can print. So typically it may convert into a PostScript, and which the printer can understand either a document or a PDF or any PPT or any other format. But the printer in turn, your drivers or in turn, or it is getting, say, decoding into a PostScript form, and the printer can able to understand this document or any other similar way where your additive manufacturing machine can understand only the STL file. So you can come from either through a CAD modeling or medical scanning or reverse engineering or any a repository system which you have come from, and then you have that data, but it should be in the STL file format. Whether you follow any methods, typically 3-4 methods are there, but your data should come into an STL file. So the STL file, typically a design data consists of geometry, of course, that is dimensions or the coordinates. Basically it's a 3 dimension, so then we need to have a 3-dimensional geometry, and typically it should represent the color, it should represent textures, and if that model consists of some textures, and of course it should represent the material that it's going to be. But unfortunately, your STL file does not contain all this information, but typically it contains only the geometrical information. So it doesn't support color, it doesn't support texture, it doesn't support material even. So, but then you may wonder why the additive manufacturing machines can print in different colors, can print in different materials, multiple materials, functionally graded materials, but how it is possible, right? So then you may switch on to the other file formats, or even it can be another third-party software may have, or some converters may have to convert your STL file into another file format like .obj or .mtl. So it can be an object file, or it can be a material file, which it consists of colors, it consists of textures, it consists of material information. But keeping in these in mind, and then ASTM, that is American Society for Testing and Materials, so they have come out with the .amf file format, and parallelly Microsoft has also developed a new file format called .3mf. But either it is a .3mf or AMF, definitely it is going to the file format which consists of all this information apart from the geometry. But unfortunately, STL will have only the geometrical information, but whereas these file formats will have more information than STL file. So then typically, what is an STL file we are talking about? So a typical STL file consists of a triangular mesh, basically. If you take a simple cuboid, so you have 6 faces. On each face, you have 2 triangles, means totally 12 triangles. So they're a typical cuboid. And if you take a sphere, of course, sphere is a geometry is not a flat geometry like a cuboid, and where you may have more number of triangles to represent your sphere. And if it is some other geometry, and it may have a different number of triangles. So basically, it is a triangular mesh, something like your finite element mesh, but the element, it is a triangle here. Why triangle? So triangle may be the simplest form of all polyhedra, which it will start, polyhedra will start with the 3 sides, that is triangle. And then, of course, you may have 2 formats of STL, that is ASCII and a binary. So if you try to save your file into an ASCII format, so which you can typically having the vertex. Basically, you have a 3 vertices and 1 normal, so which is perpendicular to the surface. So basically, normal is a vector. So you have the vector coordinates, and then you have the triangle vertices, and being a 3-dimensional coordinates, you have x, y, z coordinate for v1, v2, v3, and so on. This is one typical triangle, and it consists of 12. In this case, it may be 100, thousands, or let it be, but it consists of all the coordinate information once you save it in ASCII format. So this is a typical STL file. And of course, along with these normal information also will be there. And then it has to follow 2 rules. One will be the right-hand rule. Another one is the vertex to vertex rule. What do you mean by right-hand rule is, so then your triangle may belongs to an interior surface or exterior surface. So then if you see the sense of notation, so how do you distinguish an interior feature or exterior feature where a particular triangle belongs to? So then the right-hand rule will address such kind of thing. So your interior surface triangles should have the clockwise convention, and exterior surface triangles should have the anti-clockwise convention. And then there is one more rule called the vertex to vertex rule. So what is this vertex to vertex rule is all about? So you must have a common edge. So you have 2 adjacent triangles, and you must have a common side or a common edge. So otherwise, it won't satisfy the vertex to vertex rule. So then any typical STL file, it must satisfy this right-hand rule and the vertex to vertex rules. and then first we'll discuss about the advantages, and further next we'll discuss the disadvantages or the challenges and how it is getting addressed with the new file formats. Yeah, so that's the intention of this session. So then first of all, we'll talk about the advantages of STL file. So the advantages, of course, it is easy conversion. Why it is easy conversion? As I already said, the triangle element is the simplest among all the polyhedra, and it's basically, and these triangles are a planar triangles. It's a flat triangles, so it's very simple to represent your STL file of any complex geometries. So easy conversion, it can be done with the triangular mesh, and wide range of inputs, like almost all the vendors, the software vendors, or the CAD/CAM CAE tools. So this widely adopted STL file is widely adopted. You have a triangulation algorithm. So basically, how it will work, how it is getting saved as STL file. So in turn, you must have an algorithm, so which is a surface triangulation algorithm or a tesslated algorithm. So that tesselation algorithm or a surface triangulation algorithm, so will represent your entire model in terms of a triangular mesh, a planar triangular mesh. So, but all the CAD packages, you have this algorithm that incorporated. So wide range of inputs or wide adoption of this format, and simple slicing algorithm. Why? Because STL file is not the goal. It is not the destiny, basically, right? That is the start point. Representation of your CAD model is the start point. And what is the next step we need to do? We need to do a slicing into layers. So while slicing this, so if you're using an STL file, so the math involved in this is very simple. So every time your slicing algorithm will pick the intersection point of your the slicing plane, so that is touching your triangle facet. So the STL file, every time you are working with only the a planar edge, not like a NURB surface, or not like a B-spline in case of a free-form surface. So that's very simple to use a slicing algorithm to get the slicing points. So it is mathematically, it is very simple, and computationally also it is very simple. So your slicing algorithm will become very simple because of your STL file. And you have another advantage: we can split the model into number of parts. Then basically, why do you want to split the STL file, or why do you want to split the model? Yeah, of course. Why? Because my additive manufacturing machine have a limited build volume, but my CAD model have bigger size. Then of course I am looking for only 1:1 size. So then I don't have any option. Then I need to split the model into number of parts and then fabricate it, and further it's getting joined. So if it is an STL file, the splitting of the models into different parts, it will be very easy. And with that, some of the advantages, then we'll talk about the problems in this STL files. The problems, so basically, we can divide these STL file problems into three categories. The first category is like by the representation. So why? Because so this is basically you are representing your product or the model into the triangular boundary. So it's an approximation process. The representation itself, it is you're approximating the model. So if you have a curve, so curve is no more curve once you convert a STL file. Why? Because your curve now is become the triangular edge. So then it is by representation. So then this is the problem that we can talk about because of approximation technique. And then you may have the problems which are intrinsic to the STL format, that is file size, truncation error. We will discuss one by one. This is intrinsic to the STL file format, and maybe your conversion algorithms or your tessellation algorithms your transferring algorithm which is there in your CAD system may have proven some kind of problems, maybe some gaps in your mesh, maybe some internal walls or some degeneracy, or that may be the geometric or topological degeneracy. We'll discuss in length what are these problems and some incorrect intersection of your triangles. So then we'll discuss one by one. So the first one is by the representation. So as I already said, you have designed some surface in your surface modeling software, or typically in any one of your CAD system. This is a .prt file, for example. If you are using Clio software, and this may be the .prt file, and at the moment you convert your .prt file into an STL file, so now your the surface, basically it is a B-spline surface or a NURBS surface, for example, which you have used some NURBS method to generate this surface patch. But at the moment you saved it as an STL file, your surface now, your surface now, it has approximated, your curve is approximated with the triangular edge. So basically you are approximating it rather than you are not transferring the 100% geometry because of the conversion. So then you may be losing some information or some data. Basically it is an approximation that is by representation. You cannot do anything, but you can manipulate with some parameters like chord height or angle control. Some extent you can control the resolution of the mesh, but you cannot 100% say approximate the curve with the triangular edges. It is not possible, right? So, but anyway, this is by the representation, and the file size is huge. Why? Because you are unnecessarily saving a redundant data in terms of vertex, in terms of normals, but that is because of the syntax and semantics of the STL file. So it may be becoming a bulky file or a huge file. So the file size may be huge. That may be one of the problems. Especially if it is an ASCII format, still it may be 3 times, 4 times. Again, depends on the geometry of the product that you are handling. But the file size may be heavy, and you may have encountered with the truncation errors. So what do you mean by truncation error? Is your designer has used a double precision real number while entering your the dimensions in your product. That is by original dimension in your CAD modeling I'm talking about. But at the moment you saved it as STL file, your double precision has truncated to a single precision real number because of the STL conversion. So that may be the truncation error, and it may have incomplete data. As I already said, it has only the geometrical information, but it doesn't have the topological information, that is the connectivity or the associativity kind of topology. Basically, when can you say it is complete model of a CAD model? When can you say it's a complete CAD model? Obviously, it must have the geometry as well as the topology information. So then only you can say it's a complete data. But it is not a complete data. Why? Because STL doesn't have the topological information. This may be the another reason the slicing algorithm may take an extra effort to sort all these coordinates. It may have additional burden to the slicing algorithm Why? Because it doesn't have the topological information. So anyway, so STL file is not a complete representation. Why? Because it doesn't support the topology. It supports only the geometry and inconsistency. So whenever you have the joining of, as we said, like in the advantage is heading, we can split the models, fine. But whenever you split or whenever you append, especially you appended two STL files, but you have a huge inconsistency tolerance at that appended portion. So that may be the another concern or the problem in terms of your STL file. And it may have inconsistent normals. Say normal should be a correct normal which is perpendicular to the surface and which is projecting outside to the model, outside to the boundary, but it should not be inside. And if at all some normals are projecting inside, it should be getting flipped. So then because of this inconsistent normal, sometimes we need to perform the flipping operation. So it may have sometimes incorrect normals. So even you can mathematically reversely calculate your normal vector from your vertices, coordinates of your vertices, right? So if you could do it, that reverse calculation, and your algorithm given the normals, so then there will be a deviation or there will be an incorrect normals. So then this is another problem which we can say talk about, and that those are the intrinsic problems. But your data conversion or transfer algorithms may prune some gaps. What do you mean by a gap? So as we discussed previously, it must have the vertex to vertex rule. It must follow. If at all, if it is not following a vertex to vertex rule, means I have some surface here and I have another surface, and at the mating surface, at the intersection of these two surfaces, so one of the triangle got missed. So once one triangle got missed here, then what could be the consequence? Then you will be slicing your model. So while slicing it, so if it is intact, means the triangles are intact without missing anything. So then you can anticipate a closed contour, means wherever you have the intersection of your slicing plane with the triangle, you pick those points. I have one point here, I have another point, I have another intersection point at the slice level I am talking about. So I have another point, I have another intersection point here, I have another intersection point here, and I have another intersection point. And again, the first point and last point, it got coincided, and then we can say this is a one complete contour or complete layer in a particular model at a particular Z height, right? So this is a typical one. So if it is free from the error, means if at all there won't be any missed triangle. If at all, if there is some missed triangle, and with that triangle, you are trying to get a closed contour. You never get a closed contour in spite. So you may fall in an infinite loop. So then once you then fall in infinite loop, or it may have some they say stray vectors and no endpoints. So then how your laser, if it is a laser driven additive manufacturing system, so how your laser has to say confined to the boundary of your cross section of a particular layer. So that is the issue. Once you have some gap and you are trying to build that model which is having some error, right? And some internal walls also, like so maybe by the designer, improper joining of one object with other object, then it may have some issue. And then the degeneracy, basically the degeneracy is nothing but the kind of error that though you have what you call the three vertices, but it may not be contributing the area of the triangle. So if it is not contributing an area of the triangle, so then you may have two possible say errors. One may be because of a topology degeneracy, or it may be a geometric degeneracy. So the topology degeneracy, it may be you have the 3 vertices, but all are sitting in the same position, right? So even though you have a 3 vertices, but all are sitting at the same location, which it may not be contributing to any area of the triangle. Maybe the case you may have 2 vertex coinciding at the same point. So that is called a topology degeneration, or even it may be other way around. Maybe say though you have 3 triangles, 3 vertices of a triangle, but all are linear. But in this case also you are not having any say what you call, it is not contributing to any area of the triangle. So then it may call as a geometry degeneracy. So then it may lead to have a topology degeneracy or a geometric degeneracy. Then it may lead to further complications while slicing, while generating toolpath. So, and then you may have some incorrect intersection. Say, as for the vertex to vertex rule and other syntax and semantics of the STL files, or the rules of the STL file, say none of the triangle, they should not overlap, or they should not intersect, basically. If at all, if there are some intersection of the triangles, so then we need to identify the cause, or the or whether it is a misplaced triangle, from somewhere it got misplaced, or is it an extra triangle. So then if at all, if you are encountering these kind of intersection of the triangles, we need to say diagnose, and we need to rectify these kind of errors. So this is another error which we can talk about. Say these are some of the errors which we can talk about the STL file and errors. So basically what we need to do, we need to say take a valid model, or the valid model and invalid model. Then how do you distinguish a valid model with the invalid model? And if at all, if we take invalid model, so you have started with 3-dimensional model, and then you're slicing it, that is a 2D, or typically it is 2.5D. Why? Because you have uniform thickness across the layers, so you may be using a uniform slicing algorithm to do that. And then you have, this is an 2.5D layers, and then finally your laser has to, or laser or your extrusion head has to deposit the material that is in a 1D scan lines typically. So then this is the case once you have a valid model which is generated by your CAD systems, or it can be coming from a reverse engineering route, or it can be coming from the medical scanning route. But if it is a valid model, and it should get a closed boundary for each and every contour, or each and every layer of your model while you are processing, or while generating the codes. And if at all you have some problem in your STL file, that's what we are talking about, some triangle got missed, then that's what it has become some gap here. And if you're trying to slice that defect, or the STL file with some error like this, and you are slicing plane as used here, and then trying to pick those intersection points and trying to join, but you never get a closed boundary, and then ultimately your laser have a definite path to close this, and then it may go away from the thing, and ultimately it may have some defect in your product, or it may have build failure also, depending on the situation. Sometimes it may create a build failure, or it may create an error in your product while fabricating it, right? So then these are some of the consequences once you can come across. And then let us summarize to say, then what are the challenges that the STL file, typically an STL file consists of. And of course, the challenge is like a duplicate information. So the redundant or the duplicate information is the one challenge, and some leaks or some uh, triangles got missed, or some leakage of the triangles, or some inconsistency in normals, or it does not scale well when you are working with high resolution meshes, high resolution models. And then especially you have some lattice structures in your model, and it may have very difficult to handle through STL file representation. And of course, it doesn't support any color. So STL is a monolithic representation, but your additive manufacturing machines can print in colors, can print in different materials, and it doesn't support the material at all, and it doesn't support the orientation. So these are some of the challenges. Then how could we address these challenges? Then the ASTM has come out with suggested or developed an standard for this data format, or standard for your data file, data kind of representation. So that is, they have named it as an additive manufacturing file called AMF. So how do you address these STL problems through AMF file format? Basically, it is an XML script. You know the advantage of an XML script. Basically, it is a format of formats, or it's a meta format. It is a text-based script, XML script. It's a text-based one, and which you can easily read your data, and you can easily write your data. You can easily parse the data, and you can easily edit you have some editing tools here, and even you can do extension, extensibility also there. You can extend the files, and it can highly compressed. So as we know that STL file is suffering from a huge, large data because of syntax and semantics of the file, but whereas here it can be highly compressed. This file format can easily compressed at the higher scales. And then see the general concept of this AMF format. It is going to be a volumetric data. It is not a mesh data in case of STL file. So mesh versus volumetric data, and of course the material information is also included, and colors also included. Colors, texture mapping is also included in our AMF file format. And it can be a material combination. It can be a grading of the materials. Like now you can come across the functionally graded materials called FGMs, right? So you can vary the composition across the length or across your various regions in your product. I need to have a different mechanical properties at one region, right? So then you can do it through grading, functionally graded grading of that. So even that can be incorporated in your AMF file format. Lattices and mesostructures, and basically it can even support some repeated instancing on the packaging, and then orientation, whatever the problems that you are talking about previous file format called STL. So it will be addressed because of these concepts, or because of these file structures. So then it can be addressed. So then how do you get addressed to your Vertex duplication or the leakages? So this is a typical AMF file format. Is an XML script, which you have some duplication, so which it can be easily addressed, and some leakages, so which you can easily parse, and you can easily editable, and you can easily identify duplications, and you can remove that, and you can identify some leakages. You can do it, and it can be highly compressed, as I said previously also. So if you take a typical STL file in ASCII format, say the same file, if you save one time as an ASCII STL file, so it may be consuming around 800 KB. But if you save it in a binary, same file, if you save it in a binary file format, of course, it may be consuming around 200 KB. But if you save it as an AMF file format, so it may be in between the ASCII and binary, so it may be around, say, 320 or 330 KB of data. And you try to compress all these three formats, and the ASCII STL will be compressed around 100 KB, and your binary may be compressing around say 50 KB, but your AMF may be compressed around 25 KB. Means one can understand the compressibility of this AMF file format. Even though originally it was in between the binary and ASCII size, but after compression, so even it has been compressed less than the binary STL file. So then it can have a compressibility, highly compressive in nature. And we are talking about the approximation, right? Previously, if you have a curve and that curve will be approximated with a triangle edge, that is basically a planar triangle patch, right? So that's though you have a curvature, but in turn, once you convert an STL file, your curvature is gone, but it is approximated with a planar edge of a triangle. But how do you get address such kind of approximation problem here in AMF? So they have come out with a curved triangle patches. So instead of a planar triangle, so it's going to be a curved triangle. So the curved triangle, it is as for your profile or as for your geometry. So you don't have a problem of approximation or error in case of the STL, previous file STL. Why? Because it is a curved triangle, so which is coinciding with your curvature or the geometry that you are trying to say save it, right? So then it will support even a planar patches also. Why it should support a planar patches? So whenever you have flat surfaces, your product consists of flat surface, something like your cuboid. So cuboid doesn't have any sense to have a curved triangle, right? So a cuboid very well can you make use of a planar patches, and then you can do it, right? So then you have a flexibility here in AMF. If you are working with the flat features, then you can go with the planar patches, or if you are working with the curved freeform surfaces, then you can make use of a curved patches. You can adaptively use this, or if you are working with some what you call curved edges. A curved edges can also anticipate it by introducing a tangent vectors. So by introducing a tangent edge tangents, so then even your the curved edges can also be addressed, and curved surfaces can also be addressed, and the flat surfaces can also be addressed, and adaptively, so it will be used. So depending upon your the geometry of your product, so it can be adaptively using this. And even it can be a recursive subdivision, like you can even divide into you can even go with a more refined mesh with the 4 power n kind of resolution. So you can keep on increasing the several folds or the number of folds. So that can be also be done here. So if you typically compare the say accuracy of a original STL file and an AMF file with the same number of triangles, then only it's meaningful to compare, right? So for the same number of triangles, the same model, if you're trying to evaluate the error proven for a sphere, a typical, take a benchmark as a sphere model. For that sphere model, you saved one time as STL file and you saved another as AMF file, and AMF with a single fold without 4 power n, that is 4 power 0 typically, and then you can go 4 square, 4 cube, 4 power 4, and keep on increasing the several folds, and then almost your error is becoming 0, or it is touching 0. Means without any error, you could even able to represent your model. So that's the kind of inaccuracies that you can come across STL, this much things, and it can be further reduced by using this AMF file formats. And then it will also address the multiple material concept. Say I have one material. Why? Because my additive manufacturing machine can build multiple materials. So then my data, my CAD model should assign different materials at the different regions. Yes, you can do it here in the AMF file format. Like I have one material, some material A and material B, material C, maybe somewhere. So then I can even describe my material choice. So then I can have that option here. Even STL file doesn't support any material thing, but here you have a multiple material representation options. And even you can grade the material. Say I have some composition, the different composition across the length. So you can do such kind of a grading of the material through the CMF file format. And I have some microstructure things which I should say represent in my model. So then you can happily do such kind of a microstructural representation. And then what is the current status of this AMF file format? So the and ASTM has found in the recent times, though additive manufacturing, or formerly known as rapid prototyping, started in 1989 time, but ASTM has formed in the recent times. That is in 2008, 2009, they have formed, and to standardize and to say develop international and as well as American standards, ISO also came into picture after the ASTM. Say ASTM in 2008, 2009, and ISO for additive manufacturing. They have started in say 2001, 2002. So then you have what you call, still people are working under developing the standards either for the data representation or for standardizing the say processes. Say it will also link to your certification, standardization, and qualification, right? Say how do you get a confidence that so you have made some say aircraft engine through additive manufacturing. So how do you ensure that who is going to certify that it's getting safe to use it for a gas turbine or airplane engine, right? So then somebody has to give a certification and qualification of that. Then who is going to give a the qualification and certification, right? So who is going to give, and then how and what basis they are going to do, right? So then you must have some standards then saying that so they have followed these standards, some ISO or ASTM standards or ASM standards or some DIN standards. And then you can say that based on this, it got evaluated, it got qualified, it got certified, right? So anyway, so that's the first step, is we need to standardize these technology, right? So anyway, so ASTM F42 and F2915 is the number for AMF file format, and still around 35-40 standards in terms of feedstock, that's raw material, right? In terms of raw material standards, or in terms of process standards, in terms of post-processing standards, in terms of application-oriented, say you have some medical devices, all right? So you are fabricating some titanium implant through additive manufacturing. So who is going to give the clearance? Means you have some regulatory body like a FDA, right? So then they have to approve your things, right? So yes, it is a biocompatible thing, and then which it can be say then of course the similar way. So if you keep on discussing this, this is the state of art. That's what I want to have some link. That's what I'm talking here as standard, certification, qualification. But say coming to the data file formats of additive manufacturing. So that is the status. but still it should be adopted. And coming to the future plans, like so what kind of future plans they are looking for an additive manufacturing file in the future on the next version, maybe version 2, and version 2 is also right now it's out. Maybe version 3 even further, they may be working out something like your step file, right? If you come from a CAD domain, you know the step file format. Similar step file format, like it's a entire product data, right? And like the same lines, so the additive manufacturing format in futures, even it can be incorporated the tolerance. So how much tolerance you're looking at, right? Like your manufacturing tolerances, like what could be there. And again, depends on the type of AM process that you're using it. But typically, even they are having to have some plans to incorporate tolerances in the AM format, and surface and depth textures and data inscription, copyrights and external references, subassemblies, process control, and non-volumetric support structures, whatnot. Like say, it could be the complete product data information, maybe non-mesh geometrical specification methods like voxel based representation or a feature-based representation, which typically you can come across a CAD files, right? The same logic can it be extended to the additive manufacturing file formats. So that is the intention. That's what they are working for, that kind of things. And this is a very big subject to discuss. Actually, so far we are talking about only the three-dimensional data formats. So far we didn't talk about the contour data or your cross-sectional data I'm talking about. So once you have the STL file, so you fix the orientation, sliced it, and you generated that code. So that code or the contour data I'm talking about, that contour data, that code maybe have a different file formats. And again, it is not yet standardized by the ASTM, but still different vendors, different, it's basically a proprietary kind of representation. Maybe you talk about Stratasys, they may have some proprietary format, and talk about US, they may have other, and you talk about 3D systems, they may have their own, say you have SLC, SLI, CLI, RPI, and then other file formats. And you may have other, anyway, this is away from the additive manufacturing when you can talk about your IGS in case of your, if you come from FEM or design packages. So then you may have IGS, you may come across, and printing scenario HPGL or CT in medical, and STEP as we are talking about in manufacturing as a complete product model data. But anyway, so then it has to have then so you may get something in your mind like what could be the counterpart, like which you every time if you try to correlate your data with the CAD/CAM CAE systems, then typically how it will differ from, right? So yeah, let me summarize, let me conclude at this point of time here what I have done for the last 1 hour 15 minutes or so. Then we have talked about the fundamentals of additive manufacturing, in particular to the design, importance of the design, digital design, in fact, importance of the digital design in additive manufacturing. And we talked about some tools, AM design tools and softwares, maybe through CAD tools, or maybe model capture tools, or maybe repository tools, or maybe medical image tools. And let it come to any one of these domains, but it should ultimately save it an STL file format. We have thoroughly discussed, and we have thoroughly discussed the advantages, problems, challenges, and how it is getting addressed in AMF file format, and some future of this AMF file formats, and the AMF in particular. And of course, what could be the future of this AM data file formats? And this is about the AM and the data file formats. But before concluding, so we have a very good facility at NIT Warangal. So we have metal 3D printer. So that is of DMP Flex metal 3D printer from 3D Systems USA, which can capable of printing in metals. And we have a couple of Stratasys make machines from that is basically for a polymer printing, and we have desktop printers like Ultimaker and some DIY kinds of printers, and we have scanners also, a couple of scanners. It is AnyScan and Scan, and muffle furnace short peening machine for post processing of this metal 3D printed parts, and we have the softwares exclusively for the additive manufacturing or 3D printing. So that is a Mimic software for medical image processing, and Magix for repairing the STL files, and Trimatic for designing the medical devices and medical implants. Catalyst, of course, this is a proprietary software which will come from the Stratasys make of machines, and 3D Expert, again a proprietary software which will work for the metal powder bed based metal printer from 3D systems. Some of the at our lab, and we have a YouTube channel also. If you are interested, then I will paste this YouTube channel link in the chat box, and then you can even visit, and if you are interested, you can subscribe also to that YouTube channel. I think I have done from my side. Yeah, it is over to you. Yeah, Dr. Prabhakaran, it's over to you, and then I'm very happy to take questions and any clarifications. Do you
Sir,
need?
this is Vishwapriya, sir.
Yeah, okay, madam.
Good session, sir. We'll take up questions and then.
Yeah, please. Please.
Participants, I request you to kindly post your questions either in the chat or you can talk to speaker directly.
This is Dr. Srinivasan here. Nice presentation, Professor Ravikumar, and thanks to the organizers.
Yes,
my question is, Professor, you told about increasing the 4 power n triangular mesh in AMF. So as we keep on the 4 power n size, our data set will increase. So finally, it will increase this file size. So have you come across any situation, and how you address those kind of configuration?
Yeah, actually, coming to the AMF, relatively it is a new file format. It is not widely adopted by the CAD vendors. So if you hardly find this AMF file format with this CAD-CAM CA softwares, but STL is all these CAD packages will have that option. But slowly now it is adapting by this CAD-CAM vendors. But coming to 4 power n, but yeah, I do agree with you, like the kind of a mesh size that is so definitely. But you have a provision, like why? Because you don't have such kind of provision in case of STL file. So every time we need to have a standard mesh size in case of STL. We don't have much flexibility to refine further your STL file mesh. But whereas you have such provision in case of AMF file format. So, but I do agree, I do honestly agree with you that there will be several challenges that we need to keep on increasing 4 power n times your mesh resolution. Yes. So, but the thing is, it is need not necessary for doing all the products, but typically where you are working for a specific requirements or specific applications where we need to.
There is a power fluctuation in the college. Okay. So that's why it is not constant. It is fluctuating. It is not
Hello.
let me break down this slide. So all of you having this thing, notebook, as I am doing of it. Show your notebooks one by one.
Hello.
Is it audible to you, Mr. Vijay?
All of you having your notebook now.
Repeat the question, sir, because it was not.
Notebook, pen, pencil, everything is there. கையில இருக்க நோட்புக்ல இருக்க எல்லாத்துக்குமே.
Hello.
Mr. Vijay Prakash, can you repeat the question, please? Because it was not quite audible. Hello. Dr. Sabari,
Hello.
Sir, I think, sir, was the question audible to you, sir?
No. I don't think so. There's a question. I think maybe some conversation is going on by mistake. I think so. I'm not sure. Like maybe saying some power fluctuation, something somebody is telling, but I don't think so. No.
Okay. Participants, do you have any other question for the speaker to answer? So if that is it, I think we'll wind off this session. Dr. Ravi Kumar, thank you for a very wonderful session. It was a very interesting session with beautiful slides to explain things, and it was a lively session too. Thank you for your contribution to this FDP, sir. Over to Dr. Prabhaharan.
Thank you so much, sir, for your valuable time and sharing your experience, particularly in 3D printing domain, sir. Thank you so much. Participants, the next session will start at 11:30 exactly. Please join at least before 5 minutes. So sorry for the trouble you have encountered today in the Cisco WebEx. So sure, it will be rectified for tomorrow session. So thank you, Professor. Thank you. Sure, we'll meet you once again in our PSG Tech. We can roam inside the Type 4 and we'll explore if there is any possibility to do some collaborative research in the field of additive manufacturing. Thank you, sir. Thank you.